Welcome everybody. Nice to have you here. Today, the reason that we are standing here is because we would like to speak about the problem that we are facing at the moment and what we will have even more in the future. I will explain a little bit more in detail later. My name is Dennis Honing. I'm working for AEP. Within AEP, we have a few decades of experience with power conversion and energy storage. And my colleague here is Ralf Dieneman from the development manager, for M&P. M&P is doing a lot of development of the power electronics, and we are closely working together for many years already. That's also the reason that we are standing here. I will give a short introduction about the presentation, and then I will give the word to Ralf Dieneman, and he will give a bit more details about the technical features. So that was a short introduction. We have the honor to be the last one before the lunch, so I assume everybody will be very hungry. So we will keep it short. You don't have to make any notes because everything will be filmed, and we can also hand out the presentation afterwards. And for any questions, please do it at the end of the presentation. So, to start with, the future of new ultra-fast charging technology. How will our future look like? That's the main question. As you know, probably have heard, the newspapers are full of it. We can see long queues, waiting queues for coming to charging the cars, and also for the cars that are charging. It takes some time before your car is charged. Batteries are becoming larger, so it also takes more time before your vehicle is charged. We now have, we see them more and more coming. We have already 750,000 cars, electric cars on the road nowadays. But does anybody know in the room how many cars we have in total in the Netherlands? 9 million. So there is still a long way to go, even though it looks like we are already pretty far, but it's only 8% of the total. And that's only for electric cars. On top of that, we will also have the heavy-duty machines, commercial vehicles, which are requiring much more power to be charged. At this moment, there are, in total in the Netherlands, we have 150,000 trucks and buses running, and about 2,000 are electrified. A major part of that are the bus industry, but especially on this part, we have a really long way to go before we are fully electrified. As you might know, in the Glasgow Climate Pact, our government and also the other politicians have agreed together that we need to be durable, we need to have e-mobility, completely electric vehicles, and in 2050 we must have 100%, and in 2030, which sounds still far away, but it can go very, very fast. We need to have already 30% electrified. So that's still quite some things to do at the moment. And the Netherlands is, as many times, we are quite ambitious. So our government said we want to be completely EV in 2040 to make it even more challenging. So that's our first challenge. The second one that we have is the grid. At the moment, the grid is producing for the entire grid in the Netherlands, we are producing 120 terawatt hours in a year. If we would make, if we want to drive electrically, fully electrically, complete mobility sector, that would mean that we need about 20 terawatt hours more. That sounds like a possible thing because we still have some time, so that should be possible. That is not the real problem. A little bit bigger problem is the power that is needed. If we want to charge all the cars at the same time, So assuming that we will have 9 million cars and all the buses and trucks electrically, then you would need more than 100 gigawatt. And at the moment, our grid is producing about 31 gigawatt. So this is a huge problem that there is at the moment. Besides that, we have also the fast charging systems, which are not taken into account. Fast charging systems is a bit different story. Everybody wants to charge the vehicle in a short time. So we know it should take about 20 to 30 minutes maximum to charge the car to continue. We have taken assumption within our organization and we did some studies. And for an example, now we work out a charging station, let's say when we don't have any fuels anymore. So you want to charge many cars and trucks at the same time. An average charging station is about 20 charging place for 20 electric vehicles. Would mean that we have need 3 megawatts of power. And let's say for commercial vehicles, you need about also 3 megawatts, so in total capacity of 6 megawatt hours. If we multiply this times 2,900 charging stations, that's what the government would like to have in the Netherlands, it would mean we would have about 10 gigawatt only for fast chargers. That's 1/3 of the total capacity. So that's a bit the challenges that we are facing at the moment. And that's also the reason that that we need to work together to find a solution for it. We have worked on a solution where we would like to present to you. But before we do that, I would like to go back to the conventional technology that we use nowadays. As you can see, this is how we were doing it so far. This is a 120 kilowatt charging system where we just have a transformer for galvanic isolation. We can feed from an AC grid and feedback, provide energy to the batteries. If you look at the cabinet, you see that there are many components. Starting with the transformer, which already takes a large part, which is also always an expensive part. And then you need several components like switches, monitoring systems, and power converter. We want to make a new development to make this smarter and to reduce the amount of components that are needed. So our improvements that we wanted to make after making a study, we saw that these are the points that we needed to renew. So the actual system had to be reduced in 50% of the total size. The noises, nowadays you see most fast charging stations are next to a highway, but in the future they will also stand maybe in urban areas or in city centers. You don't want to have these noise. Usually you get like a high switching frequency noise that you can hear. So this must be reduced. And we specified that a quiet street would be sufficient, so below 50 dB. Also, the scalability is an issue. We need to go to larger systems. So for a megawatt charging system, you want to have at least 750 kilowatt, but also scalable for higher powers. Then the system must also be supplied. Sometimes we have an AC connection on the grid, but not sometimes you want to have a DC grid supply. So it should be interchangeable. That makes it also possible to add energy storage or renewables if that's needed. Another point that we want to highlight is the maintainability. When we are when we want to scale up, you must have plug and play system. So it should be easy to, when you have to service it, stack it out, put a new one in, and ready to go again. So these are the points, our requirements that we have specified. And now I will give the word to Ralf. He will explain a bit more how we have interpreted these requirements. Okay.
Yeah, I would also like to welcome you to our presentation for this event. I think Dennis had positioned some tough requirements here. I really had to do our homework. And yeah, let's see what the approach to meet these requirements can be. If you look at the design requirements, like 50% smaller design or less, even less, then we would need to substitute the 50 Hertz transformer. It's if you saw the picture, it's really the largest part in the cabinets, largest and most expensive part. For the noises, we would really go with other semiconductors like silicon carbide semiconductors to reach higher switching frequencies, more than 16 kilohertz, for example. Yeah, then for the high power requirement, we need to stack power intelligent, like yeah, look into a size for example 425 kilowatts each, and then look for a modular design that we can put them in parallel and yeah, to achieve the 750 kilowatts power. Yeah, for the AC or DC supply, we have to look for a more flexible design. And yeah, 2 types of converter modules. And yeah, by looking at the efficiency, this is the most interesting part. To reduce the size, you always have to reduce power losses. Otherwise, you can't get smaller in design. So you have to look at switching losses, for example. And this is also can also be done by other semiconductors than in the conventional technology. Yeah, for the energy storage capability, or for example, also for photovoltaic powered, we would need to have a look into DC link connections, so to connect it directly into a large DC link. Yeah, and then for the maintainability, we need less parts and good and easier accessible parts. Yeah, to stand out the keywords, at the end, we are looking for a compact design, low noise, high power, and so on. Let's see how to meet this. A state-of-the-art solution, this is what the most fast chargers and ultra-fast chargers use. We changed the 50 Hertz transformer. You see it's heavy, it's big, and exchange it with a mid-frequency transformer. So now the topology is that we use a grid input, and we have a boost converter in front. We generate a square wave bus, and then we go to the mid-frequency transformer. This example, 30 kilohertz. And then with the square wave signal, we go back to, with inductance, we go back to the DC side on the output. And then what is achievable? We see here the comparison. If you higher the frequency of a transformer, then you can reduce the size a lot. For the same power input, you just need really less of the material weight and also the size. So this can be helpful to achieve these requirements. Let's see, you can get compact design, and also the noise we fulfill because we are going up to 30 kilohertz. You won't hear it. It's out of the audible range for humans. So already check mark on this. If we look into the modular design, less parts, let's have a look at the total system now, or the first part of the system. To feed in from a DC supply, you need a bit more components than the DC-DC converter. At first, a pre-charge unit. This gives you the possibility to remove the converter to switch off its input voltage and be able to remove it from the DC bus. So here you see smart graphics that can show how this converter should look like or can look like. Then we have behind the pre-charge unit, we have the scalable DC-DC converter with the DC input side and about 125 kilowatts of power stack size. Then on the lower part, we have the DC output. We can increase the power due to parallel operation. And behind the converter, there should be some output switch to be able to power the charge point. And for the output switch, we have also some interesting solution. At the end, we have modular assemblies. And we meet high power modularity due to parallel operation. So now let's have a look at the flexible connection, the switch box on the output side, as I mentioned. If we look into the graphics and we see, okay, we can power 2 charge points with one device, but this is not the only option. We have another option with the switch box. We can power also 1 charge point with more converters, connect them together, or we power 1 charge point with some converters and a second one with another converter. So we are already flexible in the connection on the output side to fulfill also the smart charging. So we do have double pole disconnection in this case. So I would say we check the flexibility. If you have a look at the efficiency of such a converter on mid-frequency transformer and silicium carbide semiconductors, we can reach an efficiency of more than 1. Isn't that good? You see the orange band around the curve. This is the tolerances. It's really hard to measure in this case. You have to have precise measurements to reach or to see what the real efficiency is. In our case, we wanted to reach more than 97%. And from the point of 30% of the power, that's the lower part, we already received that with this type of topology. So efficiency also checked. Let's have a look at the input, pretty short. We can do this on the input side as well. We use a modular converter, nearly same looking design. Also be able to connect them in parallel. And with a multi-phase converter here on the input side, we can reach real sinusoidal current consumption. Increase the power with parallel operation. And so now we can have a look at the whole charge system. What else do we need? Just short information about the input and the DC link voltage range. We do need a general control unit in order to communicate to the charging device. Speak all the protocols. And we are also able to connect converters with batteries onto the DC link and use the battery power as well to reduce power from the grid. Can adapt to different voltage sources, and we have also redundancy in the design. So from my point of view, I think we have also a good maintainability. Here you see a special design with 3 converters. They are modular. The modular converter you can take out from the front. The pre-charge unit you can reach from below the converter. The switch box also from the front. And then you can take out the fan control as well from the front. So it's really maintainable, it's less parts, and it's not looking too complex for a whole charging system. We are already in trial phase in the city of Hanover, where these types of converters are charging buses. And if you want to have more information about it, just visit us at the booth. So I will hand over to Dennis again, see if I did my homework.
Thank you. Yeah, we let the audience decide that if you've done your homework. Yes, so as you could have seen, this is one of the projects that we have realized, and a project that might be a charger which can be applied for the future, so a future-proof charger. Still, we need to make some developments and next steps. Of course, we want to make connection to renewable systems or maybe fuel cell, and also a vehicle-to-grid functionality, which is getting more famous because you have a big battery. You can do much more than it than only use it for your vehicle. So support the grid maybe also. So that are parts that we still want to develop, and everybody that can help with that, we will be happy to discuss this in more details. So thank you very much for being here in the presentation. I hope that you have had an interesting presentation about our systems, and that we can have further discussions during the lunchtime, or maybe you can visit also our booth where we have one of these units present so that you can see it. Thank you very much.